We say that we use integration by parts when we use this identity that you see here. This identity can be proved if we use the rule of derivative of a product of two functions u and b. But here what is interesting is that it's always the case that when we are computing the integral of a function, this integral always can be considered as the product of a function multiplied by the differential of another function. This differential of the other function could be just dx, and it will be always the case that the integral of the function multiplied by the differential of the other function is equal to the product of the two functions, now without any differential, minus the integral of the function that have the differential in the original expression, multiplied by the differential of the function that doesn't have differential in the original integrand. So if we do that, if we express an integral that is written originally in this way, and we express it in that way, and we observe that the new integral that we obtain is easier to compute than the original integral, maybe this can be computed using a basic rule of integral, or maybe it can be computed in an easier way. Anyway, if this integral can be computed now in an easy way, after we compute this integral, we say that the original integral was obtained by integration by parts. I'm going to show you two examples in which we use this idea for making the integration of a function. For example, if we need to compute the integral of x e to the power x dx. So we observe that if we have a function like this, we can consider that this x e to the power x dx is actually u multiplied by dv. What will be u and what will be dv? Here we can think that this u is this x, for example. So I'm going to say that u equal x, and dv could be the rest of the expression e to the power x dx, e to the power x dx. I understand that can be written in a different way, can be considered in a different way. For example, I can consider that u equal e to the power x, and dv it will be x multiplied by dx. Or maybe u equal x to the power ex, and u equal just x. So there will be many ways, but if you find a way in which when you write the integral in this way, integral of b du, and this integral is easier to compute than the original integral, then we are going to say that we are using integration by parts. Okay, so let's see that u equal this x and dv equal e to the power x dx. Observe that we need to know what is du. So if u equal x, then du, the differential of u, then will be the differential of x, obviously. So du equal dx. And also, if dv equal e to the x dx, if we know the differential to know b, we need to get the integral. And I know that the integral of e to the power x, it will be equal to e to the power x. This is one of the rule of integration. So I'm going to say that v equal e to the power x. And now we are going to observe if this integral v du is easier to compute. So, and v du, this is b, and this is du. So, e to the power x dx, definitely this will be an easier integral. So, this works only if the integral that you obtain is easier to compute than the original integral. So we don't know how to compute this integral, but maybe the new one will be easier to compute. So let's see. Let's write then what will be, using integration by parts, what will be this integral of x e to the power x dx. So the integral of x e to the power x dx, using integration by parts, it will be uv minus the integral of v du. Okay, so using the formula of integration by part. And u is x, and v is e to the x, so here will be, this uv will be just x ex. Minus the integral of v du. Here we have v, and here we have du. v is e to the x and du equal dx. So minus the integral of e to the x multiplied by the differential of x. And I notice that this new integral is easier to compute than the original one. So it doesn't have the x. So this idea can be used anytime that you have e to the x in one of the factor of the, and the other is a power of x. So the new integral will be easier to compute than the original integral. This was using just integration by part, and this integral can be easier compute using the rule of integration. The integral of e to the x, we can review all the rules of integrations, and we notice that this is e to the x. So we can write x ex minus the integral of this, that is e to the x plus c. So we can write x e to the x minus e to the x plus c. I know that at the end I need to add a constant of integration. So we have used just the integral of the exponential function rule. That is one of the rule of integration. And we can, for example, noticing that this is a common factor e to the x, we can write this that x minus 1 multiplied by e to the x, so a common factor plus c. So this is just factoring. We have solved the first example. Let's solve another example. Compute the integral of the natural logarithm of x dx. We don't have so far a rule for computing this integral, but we notice here that there is only one option to choose for u and dv. Remember that using the integration by part, what we are going to do is find a function u and v in such a way that the original integrand can be written in the way u and dv. And the only option here will be u equal the natural logarithm of x and dv equal this dx. So we can say then that u equal the natural logarithm of x and this dv will be this dx. And obviously, if u equal the natural logarithm of x, then the differential of u, remember that the differential is the derivative multiplied by the differential of the independent variable. So the derivative of the natural logarithm of x is 1 over x, is one of the rule of derivative. So the differential of u will be 1 over x dx. And if dv equal dx, then v will be x. The v and x will be the same. So for computing the original integral that we have here, what I'm going to use is use the formula of integration by part. Remember that the formula is uv minus the integral of v du. So it will be u multiplied by v minus the integral of v du, the two functions that appears here at the bottom, v and u. And you notice that v is x and du equal 1x over the x. So now multiplying this v and du, you are going to get a function that doesn't have this natural logarithm that we have at the beginning in the original function. So we have here then that this will be uv, so we multiply here this in diagonal here, x and natural logarithm of x minus the integral of v du, so x multiplied by 1x dx. This is what we call integration by part. And obviously this x multiplied by 1 over x, we cancel the x and we have just the differential of x here. So we have that this is x natural logarithm of x minus the integral of the differential of x. And this new integral is very easy to compute. So we know that the integral of dx is just x plus the constant of integration. So we have that this is x natural logarithm of x minus x plus the constant of integration that we need to add at the end of any integral. So this is then uses integral of 1 rule, because this is like the integral of 1, that we know that the integral of 1 dx is just x. And just if you want, you can get a common factor here, x that multiply the natural logarithm of x minus 1 plus the constant of integration. And we have obtained, by the way, another rule of integration. The integral of the natural logarithm of x is just this x natural logarithm of x minus x plus a constant of integration. This is obtained using factoring. But obviously, this expression, the previous one, is a good expression for the integral of the natural logarithm of x dx. So we have actually obtained a new rule of integration, and this new rule of integration, we can say the integration of natural logarithm of x. So the new rule says that the integral of natural logarithm of x dx will be x natural logarithm of x minus x plus c. This will be the rule for the natural logarithm of the integral of the natural logarithm rule that we can use later in another integral in which this natural logarithm appears as one of the term in the integral. Okay, with this I have explained these two first problems using integration by parts. I hope you have found them useful. Thank you.